Herkese merhabalar. Öncelikle bizi tanımayanlar için çok kısa kendimizden bahsedeyim. Ismosys, elektronik komponent temsilcisi bir firma. 20 civarı üreticinin biz burada temsilciliğini yapıyoruz. Tasarımdan satışa ve hatta ödeme operasyonlarına kadar entegre bir çözüm sunuyoruz. Bunun için tabii distribütör partnerlerimiz de var. Burada bugün standımızda partner firmalarımız olan örneğin Bell Power, özellikle power çözümleri, endüstriye yönelik niche power çözümleri, yine connectivity çözümleriyle pil ömrünü uzatan veya pil gerektirmeyen uygulamalarda çözümler sunan Atmosik, minyatür audio komponentleri, soğutucu uygulamaları, fan uygulamaları, bununla beraber konnektör çözümleriyle CUI firması ve son olarak da IoT uygulamalarınızda güvenlik çözümleri, security microcontroller sağlayacak Wisecave firmasıyla partnerlik yapıyoruz. Aslında videonun, yani görselin kendini daha iyi anlatacağını düşündüğümüz için bunlarla ilgili size kısa bir video hazırladık. Ben geri çekileceğim ve sizler videoyla baş başa kalacaksınız. Daha detaylı çözümlerimizle ilgili bilgi almak isterseniz de sizi 7E12B'de standımıza bekliyoruz. Çok teşekkür ederim. Sağ olun.
Welcome, and today we are going to be talking about the difference between absolute and incremental encoders. Before we jump into the differences between the two types of encoders, let's quickly review what an encoder is. With most motors, you provide power and it spins, but there is no feedback to let you know how many times the shaft is rotated or what position it ended up in. An encoder is something you can integrate with your motor to provide that type of position feedback. Using various methods, it measures how much the shaft is rotated and sends this information to a controller of your choice. With an incremental encoder, the output typically has two square waves on individual channels that are output 90 degrees out of phase of each other. With the two square waves offset by 90 degrees, as the encoder rotates, it is possible to calculate which direction the shaft is moving by looking at the order of the incoming signal state changes. Those same signals can be measured to know the speed of the rotation and the distances traveled. With a little math, it's easy to even determine the shaft's angular position. To associate the output of the encoder with real numbers like RPM, the position in degrees, or how far the shaft has turned, it is necessary to know the encoder's resolution. Resolution can be described in three different ways: pulses per revolution, or PPR, counts per revolution, or CPR, and lines per revolution, or LPR. As resolution is notated differently across the industry, it's important to get the numbers into the same format when comparing products from different encoder manufacturers. For example, pulses per revolution describes the number of high pulses, or periods, an encoder will have on either of its square wave outputs over a single revolution. This is distinguished from counts per revolution, which looks at the number of total states that occur over a revolution. Since each signal switches between high and low states, and there are two output signals, you end up with 4 distinct states for every period. This is referred to as quadrature decoding. If the resolution of the encoder is 1024 PPR, there would be 4096 CPR after quadrature decoding. That is to say, there are 4096 state changes in a single revolution, or 4 times the PPR. Lines per revolution references the lines either printed or etched on a typical optical encoder disc, and is the same number as pulses per revolution. Again, naming conventions may be different depending on the manufacturer, so if you are uncertain and want to confirm that you're comparing things properly, I recommend looking at the datasheets and examining the waveforms themselves to verify. Now, while the information provided by an incremental encoder is incredibly useful, there are some drawbacks due to the fact that they only measure relative movement. They only provide information if there's movement, and if there's a loss of power for whatever reason, the current position becomes unknown. They also require constant monitoring, and if there is noise that either causes a pulse to be missed or a false pulse to be counted, the position would be off and need to be reconciled with some sort of index pulse. However, all of these drawbacks are overcome with an absolute encoder. An absolute encoder uses an optical, magnetic, or capacitive sensor to identify unique positions within a motor's revolution. With these sensors, as soon as you switch on the encoder, it knows exactly what the position of the shaft is and will transmit that data digitally to your controller, usually over a serial interface, without needing to rotate the shaft. Instead of simply counting how far you're moving in one direction or the other, like with an incremental encoder, the absolute encoder knows its current position at all times. From this, speed and rotation direction can be easily derived. Interestingly enough, there are both single and multi-turn absolute encoders. Multi-turn encoders not only give the absolute position of the motor shaft, but also actively track the number of rotations the motor has made. For both single and multi-turn encoders, the resolution of these sensors is usually specified as the number of binary bits available per turn. For instance, a 12-bit encoder would have 4,096 unique positions, similar to the number of states in the 10,024 PPR or 4,096 CPR incremental encoder described earlier. The difference, though, is that the positions of the absolute encoder are each unique, and with a simple calculation, you can convert the binary position value to an actual angle in degrees. While incremental encoders are slightly less expensive, they also require more hardware and software processing to convert the pulses to useful information. This adds even more complexity when you're using multiple encoders in conjunction with each other. It is much easier to combine multiple absolute encoders into the same system with their various serial bus interfaces that they support than it is to put multiple incremental encoders in one system when each incremental encoder requires its own unique quadrature interface. As the price gap between absolute and incremental encoders continues to shrink over time, absolute encoders are becoming more and more popular. While almost a requirement in all robotics applications, absolute encoders are becoming more common in other industrial and even consumer markets, such as with camera motion control, egress control, and more. I hope you enjoyed learning more about encoders and the differences between absolute and incremental versions. If you have any more questions about encoders, check out our motion blogs on our website.
In Ismosys, we are pioneering the lowest power connected solution in the industry to enable the forever battery and battery-free IoT. It's projected that in 5 years, there will be 35 billion installed connected devices worldwide, each with at least one battery to be recharged or replaced. Our vision is to radically reduce the IoT's dependence on battery power. With our lowest power radio and on-demand receive innovations, we lowered the power between 10 and 100 times. By radically lowering the power requirement, energy harvesting is a viable source to power connected IoT devices to enable battery-free operation. Ismosys M3 chip is just our first step towards our vision to enable the battery-free Internet of Things. Let me show you how the Ismosys M3 chip powers this wireless connected keyboard, completely free of external batteries and dependent solely on harvester energy. This keyboard contains our Bluetooth design featuring our M3 chip that enables energy harvesting. This is the RF energy source connected to the USB port that powers the keyboard. I'm going to remove the batteries that typically power the keyboard. You can see I'm typing with the keyboard now. Powered solely by the M3 chip with energy harvesting. Ismosys M3 chip is just our first step to enable the battery-free Internet of Things. We welcome the opportunity to help you build your own forever battery or battery-free IoT products.
Bell Power Solutions e-mobility product family includes power conversion products for e-mobility applications. The product family includes inverters, converters, and chargers that are automotive compliant, IP67 sealed, and have full galvanic isolation. INV series are 6 kilowatt DC to AC inverters that provide 120 and 240 volt AC outputs to drive AC accessory loads from the high voltage DC bus. The inverters can also be used in parallel for up to 36 kilowatts of total output power. The DNC series are DC to DC converters that can be used to power low voltage accessories from the high voltage DC bus in hybrid and electric vehicles. The 4 kilowatt DC to DC converters can provide 12 or 24 volt DC outputs. The BDC series are 7.5 kilowatt bidirectional DC to DC converters that can power 12, 24, or 48 volts DC accessories. And they can also be used in reverse, supplementing the high voltage bus from the low voltage side. INVCH series 15 kilowatt bidirectional inverter chargers combine inverter and charger functionalities in a single unit. This allows for AC to DC power conversion for onboard battery charging and DC to AC conversion to power 120 or 240 volt AC accessories. BCL series battery chargers are 25 kilowatt on-board battery chargers for hybrids and electric vehicles. 4 units can be used in parallel for up to 100 kilowatts of charging power. They can operate from a single or 3-phase AC input and output from 240 to 850 volts DC. Bell Power Solutions also offers custom solutions, including modifications to existing products or full customization of performance and packaging. To learn more, visit bellfuse.com/powersolutions.